Looks like we're just about there, folks. Kind of a light class, but I kind of expected it thanks to sports and Valentine's Day. It's kind of just a weird spot to be in the class so far. But I appreciate you all making it, whether in person or in Zoom. Well, it's official. Looks like we can get started. So welcome back, folks. Well, I have returned some exams, but we are faced with the reality of the Pocatello Testing Center can get kind of easily swamped, especially since all of my exams for all my class, not all of my exams, but all my classes have quite a bit of exams going towards them. So I'm still waiting for them to scan their set of exams and return to me. I believe that should be happening sometime during this work week. So I should be grading your exams and getting them returned for those taking them in the Pocatello Testing Center. I'd say by Friday at the very latest, but I'll keep you informed on what's going on with their workflow. Give me one moment. Once the exams are all graded, I'm going to be posting some summary statistics right here. I'll also post the solutions to the exam right above this exam one information right here, so you'll know what all the solutions are. But any other questions about the exam or otherwise, folks, at the moment? Okay, well, with where we're at to the course so far, we're working through section 6.1. We may finish it today, and if so, I'd say that due date is official. If not, we'll push it back by a couple days. Once we get through that section, we'll be getting into section 6.2. And I put this document down here early. This is the one I thought I uploaded, but it's here early because this is the document I will be definitely posting on exam 2 for your notes. So when we plot our trigonometric functions, this turns into the overall cheat sheet for everything you need to know to make your plots go through. So what's on this document is information about how to get amplitude, period, phase shift, when your cycle starts, and all sorts of good stuff. This tells you the right increment, where you need to put your values on the x-axis to get to all the interesting pertinent information. And also has some color coding there. The red is going to tell you things that are unusual. What's unusual is sine and cosine of amplitude, but neither of the other 4 functions do. And some of them are tricky for different reasons. Tangent and cotangent do not have period 2 pi, and so our modifications we make here are different than we'd expect. So a part of our goal in section 6.1 and 6.2 is breaking down this information, seeing how it works. But one thing you do have to memorize for the purpose of the exam is we need to know what these original plots actually look like in order to plot their transformations and using this information down there. So the major memorization on exam 2 is knowing that these basic shapes of the curves. This stuff will be provided to help you sketch any transformation. So in other words, we need to know that sine starts at the origin, begins increasing and going on its way down. And one thing that's kind of interesting is we said the period on this is 2 pi. If we want to calculate this as efficiently as possible, we'll later on say that the increment that we need to use is equal to 1/4 of the period, or 1/4 cycle is what it might be indicated as. That'd be 1/4 times 2 pi. And this simplifies to a pi over 2. Pi over 2 is really special to this function because at pi over 2, we hit a maximum. Add pi over 2 it again, we have a value on the x-axis. Add pi over 2 again, we hit a minimum. And likewise, add pi over 2 again, we hit the x-axis. So that increment, 1/4 of a period, turns out to be magical. We really are only needing to plot 5 points. We know the basic shape of the sine wave, and so we use that to our advantage. And that's what's going on right here. 1/4 of the period is how you're going to plot this as efficiently as possible, not necessarily plotting down, I don't know how many points that is, of dozens of different points. Well, let's put that to action. Next graph we're going to plot is cosine x. Any questions, folks, before we take a look at that next one?
So do we need to know about the increment thing? Like, is it gonna be on the test and all that?
It's going to be provided right here. Yes. So as
Okay.
far as like memorizing it, it'd be good too, but if it's right here, it's always going to be available as well. It's more about we need to know that that's kind of the most efficient way to go about the plot. Any other questions so far?
Thank you.
Yep, you betcha. Okay, let's turn this over to cosine. Let's give this a try. So we expect the period of cosine is going to be 2 pi. So let's say here, if the period is 2 pi, the most effective way we're going to plot this function is by taking 1/4 of that period. So a fourth of period. This will be a fourth times 2 pi once again. Now let's show the cancellation. Simplifying this is just taking this 2, canceling into that 4, leaving a 2. So we've got an increment of pi over 2. So for plotting with that as an increment, we'll start at 0 and at 2 pi, and the increment is what we just calculated at pi over 2. So let's put all this into action. Here's our plot to start us off. One long horizontal axis. Usually it's a shorter vertical axis. We have a maximum height of 1, a minimum height of -1. And let's start putting down the pi over 2's. We're starting at 0, so our first point is really here. Next, it's at pi over 2. Add pi over 2 again, and you have 2 pi over 2. Now that looks funny, right? It's really just pi. If you like to simplify it, no harm done. I think for a lot of people, not a bad idea to just leave it like this, because the next value would be 3 pi over 2. Next value is going to be 4 pi over 2. And that one would simplify to 2 pi. I think a lot of people find not simplifying these values is not a horrible way to go. It can make some of our work more efficient, especially if these are kind of more awkward fractions that we're dealing with. So I'll leave them unsimplified. Next thing we're going to do is calculate cosine. Let's maybe use a color for that. To start off, we're now going to the unit circle, and right over here, we need to recall what is cosine at 0. Any volunteers for that first function output?
Is what?
Yes, good call. This one comes out as a 1. And so here's the memorization for this one. Cosine is going to start at its maximum value. If you put a -1 right here, it'll start at its minimum value either way, otherwise. But for ordinary cosine, here's where we begin. Next, we need to calculate cosine at pi over 2. Any volunteers for at pi over 2 for cosine? Exactly. This one evaluates directly to 0. So we start at our maximum because we're incrementing by 1/4 of the cycle, or a fourth of the period. We're hitting the minimum next. Or excuse me, we're hitting the x-axis next, and then the next value, we should expect it to be a minimum. But let's just write this out to convince ourselves. 2 pi over 2 is just pi. So we're really looking at cosine pi. Sure enough, that really is -1 on the unit circle. So on this one, it drops down all the way to -1. At this stage, you probably know what to expect. It should hit the x-axis here. Let's write it in. Cosine 3 pi over 2. Yes, in fact, that is 0. That's where sine takes a value of -1. But cosine is 0 directly there. Last is 4 pi over 2. That one simplifies to 2 pi. But for calculating cosine at 2 pi, that is exactly the same as calculating cosine at 0. Those angles terminate at the same exact location. So they both output a 1. So right here at 4 pi over 2, or 2 pi, we have our maximum height again at 1. And the curve would look like this for cosine. It's kind of a tricky one to draw. Let me try again. Up here, it starts to come down. When it goes through pi over 2, it's decreasing at its fastest, but then it levels off going beyond there. Starts to increase, and it increases at its fastest around 3 pi over 2, then levels out beyond. And this is one cycle, or one period, of cosine x. So we did it, folks. If you compare how we did our sine function, it's a little bit more work, right? We decided we were going to go by 45 degrees. That's working pretty hard. But for the plots we're doing, 1/4 of the period, that turns out to give you everything you want. Maximum values, x-intercepts, and minimum values are all found at these locations. Well, it's also asking us to state the period and amplitude of g, or g is cosine. So we can say here, period. Oftentimes we'll just call that p for period. If this curve keeps on going, it just replicates in the same way. Here's the visual. If I kept that same shape going, this is what it would look like. That means from here to here, that's the minimum length that you have to draw to get an entire cycle. 4 pi over 2 simplifies to 2 pi, and so that tells us the period of this thing is 2 pi. Next, we need an amplitude on this thing. Anyone recall what the amplitude should be for a curve like this one? It wouldn't be 2, but you're on the right track, definitely. What's unusual about definition? Yes, it would be a 1. For our definition of amplitude, we're going from the midline to a minimum or to a peak. 2 would be just the full from min to max. So in a way, you've got the right idea of amplitude. In our course, we usually just write it in as a 1 for this kind of stuff. So that's the period and amplitude. For domain and range, it's exactly the same as the sine function. Domain is all real numbers, so we'd say domain is R. Again, that's just our fancy way to say all real numbers. You could write out, if you prefer, that this is just the same as saying negative infinity to positive infinity. So domain is not terribly interesting, but it's nice. There's no problems here. You could put any number inside cosine, and it's going to output you a value. As far as the range is, it goes from the minimum of -1 to a maximum of +1. It actually hits those values, so our range is a closed set. To convey it captures -1, we use a bracket right there. And to convey it actually hits a +1, we use a bracket on the upper end as well. So -1 and 1 are included, and we're including all real numbers between those extremities. So that's the full story for cosine. That's one cycle. That's typically how we would draw it, starting from 0, ending at 2 pi. And those are the pertinent features of cosine. Any questions at all, folks, on getting through that one? Okay, like we were mentioning before, this will be available to us when we're doing our second exam, but what we need to know is the original plots like sine and cosine. It turns out plotting these functions is not too bad. It's just a recipe we have to follow. But if we're not sure what sine looks like, we might get all this information, but we'll get stuck on where to actually plot the curve. Alex asks, would there be any case in which one would use a negative, such as non-real numbers, in this section? Now, in this case, we're only going to be using purely real numbers for our sine and cosine. But that's a great question to ask, because you can put a complex number right here and make this a complex valued function. So a complex analysis, that's exactly what they do. They take all of our normal functions and they scale them up to complex numbers. But for us, we're going to stay strictly in the real number land. Oh, not negative, the parentheses. Let me double check. I'm not completely sure on your question, Alex. What were you referring to on the non-real numbers? Or not negative numbers? Oh, I gotcha. So yes, there's going to be cases where there's going to be a parenthesis right here, parenthesis right there. That's going to be in the situation whenever you're dealing with, let's show one really quick for emphasis. So if you deal with this function, y equals tangent x, this one has problems with the domain massively. Every one of these lines are vertical asymptotes, and they point to a value excluded from the domain. So to specify the domain of tangent, yes, we would have to use parentheses. because right over here, it turns out to be exactly pi over 2 is excluded from the tangent function. That's because tangent has cosine in the denominator, and cosine at pi over 2 is a 0. So yes, we will see those situations down the line in section 6.2. Other questions at the moment? Okay, well, let's get to the meat of this section, which is right here. This theorem is just summarizing what we saw from our two plots. Functions sine and cosine are periodic, and their period is 2 pi. That's the minimum length on the x-axis that you would have to plot on to get one full cycle for cosine. Amplitude is 1 on this function, and what we're actually going to be trying to plot are these sort of things. I mentioned these are all just transformations. I thought it was a good idea before we get really deep in the weeds and plot this one. Let's just play around with this arbitrary function and see what it does. So let's start with y equals a sine bx minus c plus d. We'll add sliders to every single one of these, which means these are values that we're going to change, and they're all starting at, looks like a 1 so far. Let's actually make this one be, yeah, let's make that one be a 1. I want to turn c to 0 and d to 0. It's kind of hard to do. Oh, there we go. Actually, I could just type it in, it looks like. So looking at all of this so far, let me see if I can make this a little bit bigger. There we go. There's our function. That's the ordinary sine wave we were used to seeing. We can zoom in on it, zoom out on it. And the first thing to take note is what happens if you change that a value? That's a particular transformation on the function. And it's saying here it's going to affect the amplitude. It turns out if you multiply by something here other than 1, you're stretching the curve vertically in this way. Let's show that. Let's put in a 2. At a is 2, so if you plug a 2 here, the curve is now at this height. It takes a height of 2 right at pi over 2, rather than a height of 1. So that's our first transformation. If you put in a 2, it stretches. If you put in 1/2, it's going to now shrink it down. So now it's at a height of, maximum height of 0.5. Next thing that happens is this b value. I think that one is pretty tricky because that's going to be a stretch or compression in the horizontal direction. And notice what it does here in the notes. The period is automatically 2 pi, that comes from up here. But whatever b is, you divide into 2 pi, that's going to change your period. Let's show that next. Let's let a go to 1. The b coefficient is still a 1 on this. And let's change it to 2. That should change our period to pi on this. So here it is, 2. Notice it became much more compressed, and from here all the way down to here, that's pi. So now our period is pi, all because we put a 2 right there. So anything you put here, if it's larger than 1, you are compressing the graph. Let's show that. Here it is larger than 1. Put something less than 1, but still positive, and you're stretching out the graph. The more you get it closer to 0, the more you stretch it. So that's our next transformation. Changing the value right here is changing the period. This value is changing the amplitude. But it gets even more interesting. Let's put this both back to 1. And question for the class next. What would happen to this curve in blue if we put a -1 here? Any volunteers for what should happen? Exactly. This one's going to flip across x-axis on us. So let me go right to here, plug in a -1, and that's the new picture. Notice the sine wave is going down this time instead of going up. So that means when we learn the sine curve, we need to know what it looks like if the coefficient's positive. Starts at the x-axis and increases. But if the coefficient is negative, say -2, it flips and the amplitude also increases all at the same time. That's 2 transformations happening all at once on that one. That's kind of tricky. Any questions at the moment? Okay, I'm going to bring this back to a 1 here, 1 here, zeros on the rest of them. So we're back to our original ordinary sine wave. Now let's say what happens when we affect the C. This one's called a phase shift. So the phase shift involves both C and B at the same time. But let's say B is 1, so we can just focus on what happens. What I want to plug right here is, let's say a 1. Now, question for the class, if you put a 1 there, does the curve move to the right by 1 or to the left by 1? Putting a 1 right there. It turns out it's going to go, let's see, this is the weird one. This one goes to the right, and it's extremely counterintuitive. In fact, right here on the notes, transformation of graphs, this one is from college algebra as well, but highlighted in yellow are, to me, the most counterintuitive transformations ever. If you put a negative right there, it goes to the right, and I always have to think about it because my brain is always fighting it. It just doesn't seem right, but that's what the function ought to do. If it's a positive quantity, we go to the left by that amount. So essentially, whatever is here, the negative falls off, and we move to the right by whatever C over B happens to turn out. But let's see if we can make that show. Let me see how we want to do this. I think a slider is going to work for us. So I'm going to move the slider, changing the value of C. It's just changing this quantity. If I move it to the right, oh, the thing is moving to the right. No, I think I got that mixed up. Let's see. If we have a positive quantity here, so it's a negative 3.8, it moves to the right. Did I get that mixed up with your response? Starting to get kind of tangled up at this point. Sorry about that if I did get mixed up with what we were saying. Now, if I make this C a negative, that's going to convert this all to positive. So here we are at 0. Put in, say, like a negative 1. And the whole thing should have moved now to the left by that amount. Let's move it back to 0. Yes, it really moved to the left. So when we go back to 0, the whole curve moves to the right. So putting in negative values here means we have positive values here that's going to the right. Putting in positive values means this is negative and it's now going to the right with a negative value. These are easy to mix up. The biggest thing to keep in mind is whatever happens, this negative just comes off and you're doing the transformation in the right direction if you think of it in those terms. Kind of a nasty one. That, again, to me is my least favorite of these kinds of transformations. Other questions at the moment? Okay, last one is what happens with the coefficient D? That's just going to affect the midline. That one's not so bad. It's affecting this part of the equation. If you make it positive, it goes up. So that's the thing we expect. That's the right direction. If you make it negative, it goes down. And now if it's a negative 4.6 here, that just means the whole sine wave is oscillating around negative 4.6. So that's the tour of all the transformations visualized with sliders and such. Now what we want to do is see what happens with this one if we do it just following this advice right here. Well, any questions or comments, folks, before we start taking on this plotting problem here? Okay, for this one, the instructions look kind of involved, but what I'm going to do with these instructions is I'm going to write them down verbatim on homework assignments as well as on exams. So you'll expect this kind of thing when you see it as an exam question. In fact, back for the homework, in assignment 5, the homework looks like this. You have to click on it, and it's these problems right here. The reason I did that this time for assignment 5 is our textbook is a free textbook. We have to be honest, some of those sections are not the best, and the problems from this section 6.1 are actually kind of terrible. The objective is to plot these kinds of functions, and there's not very many problems actually doing that. So these are custom set problems, and they're all pretty much how your exam questions are going to look like as well. So let's give this a start. First thing we want to do is run through the motions. It says for each given function, determine the amplitude. For amplitude, I usually paraphrase that by just saying amp. Now that we're determining the amplitude, we can work backwards from this information. It says that the absolute value of the A coefficient. A coefficient is the leading coefficient, the thing multiplying sign. So back over here, we'll take absolute value, -3. Amplitude has to always be positive, so that's why we're slapping an absolute value function on it. And it results in a +3 altogether. So that checks off the box for amplitude. Next thing we want is period. Well, that's what it's asking for next in the instructions. So here's our shorthand from earlier in the notes. We're just using P to represent period. The formula goes like this. We start with 2 pi. The reason we start with 2 pi is because we're dealing with a sine curve. And sine and cosine have period 2 pi for sure, so that's our starting point. But then the next thing we look at is, what is the B coefficient? Oh, excellent. That means we don't have to worry too much about this one. If there was like a 3 there or a 2, we would divide into it. But with nothing there, we've got it, folks. It's just 2 pi. Don't worry, we'll do one where there is a leading coefficient, so we'll see how to handle that next case. So all set on this one, we're not changing the period. Next thing we wonder is, are we changing our phase shift? We definitely are if there's something right here. So that gets conflated with this part of the problem. And the phase shift is calculated this way. Whatever the sign is right here, you always take the opposite. And that's an important enough idea. It helps us not worry about the trickiness of that transformation going left or going right. And we ought to put down a mark on this. Let me try to do it slightly better. There we go. Always take the opposite. Sorry, say again. Exactly. So we'll just get pi down here for our phase shift on this one. Sorry, say again. Well, what I mean by change the sign is this negative sign right here. So this negative is going to turn down to just saying pi without the negative sign. So on this one, it'd be a phase shift of pi. On the next example, it'd be a phase shift of -pi/3 on this one here. So we need a good shorthand for phase shift. You can always just write it out, but I think a good shorthand for this one is P dot S dot. That would make sense. So P for phase, S for shift. Phase shift on this one is just pi. Next thing, we need the midline equation. But word of warning on this one is, I don't ask a lot of questions that involve a midline. This one would be kind of a specialty one. We'll see one on the very bottom of the notes. Pi on this for phase shift. Well, it's going to be the opposite of what's right here for phase shift. So our C is the pi right here. We took off the negative sign. And the B is a 1, since there's no leading coefficient there. Oh, gotcha, yeah. Yeah, we're going to do that one next for the midline, exactly. Other questions at the moment? Okay, then again, this one's not super special, but I put on the instructions just in case we do see one that has a midline equation. So usually you're just going to say this. The midline is the equation y = 0. It's totally correct. The sine curve is going to oscillate about that, unless you put something like, say, +3 right there. Then this would turn into a 3, and that's where the curve is oscillating on, the horizontal line at height 3. But ours doesn't have anything there, so we just put 0 for the midline. Any questions, folks, to that stage? Okay, so the first thing you'll see on these instructions are find those values. And let's suppose you did make a mistake on any one of these. You might lose a single point if everything you also plot is accurate based on this information. So there's a lot of partial credit built into this kind of work. The next part of the instructions seem pretty routine. Graph the function over one period. But these are asking for specific ways to give the graph. We need the exact x-intercept. Not a decimal approximation. We need like pi/7, for example. We need the exact coordinates of the highest and lowest points on the graph. It's really asking a lot. But here's how you can achieve everything that's in here highlighted. A good plot would have those features. It would indicate x-intercepts, maximum, minimum values. And to get all of them, the next thing I would write down is this. We need to know where we're even going to start the plot. And the formula for the start of the plot is the phase shift, so P dot S. Wherever your phase shift is, that's the start of your plot. Our phase shift is at pi, so we're starting right at pi. Next, we need to know where to end it. And that's not so bad. If you're starting at pi, but your period is 2 pi, we're just going to add 2 pi to that. The full formula goes phase shift plus period. So grab the phase shift again. That one was pi. Plus, we need to grab our period. Let's color code that one in green. We found our period is 2 pi. So that tells us our entire sketch will end at 3 pi. Now, the next thing we need, probably the most helpful thing of all of them, is this. If you're doing a plot, you need to know how much you're going to increment from one point to the next. And if we want to do it as strategically as possible, this is the formula we want. 1/4 of the period. 1/4 of the period, or 1/4 cycle, however we say it, will be calculated this way. We do another substitution. It says P, so we look up the value P at 2 pi. Let's simplify this down. This turns into pi over 2 altogether after canceling. And so that's the magic ingredient that's going to allow us to hit every single thing that's indicated here in green without working too hard at all. So now that we're there, we're ready to start plotting. Any questions so far to this stage, folks? Okay, here's how the plot's going to go. First thing I usually do is I want to nail down the horizontal axis. So let's just throw it in without a vertical axis. The strategy for not putting a vertical axis is sometimes only because your vertical axis doesn't have to be anywhere near your plot. Maybe your phase shift was huge, for example. So we're going to start at pi, it says. Increment by pi over 2. Instead of writing pi, it might not be a bad idea to just call it 2 pi over 2. That is pi, that's where we're starting. Next value is going to be, we're really just doing this over and over again. Add pi over 2 to get all of the values. We should get 5 tick marks altogether on our plot. So next it's 3 pi over 2, 4 pi over 2, 5 pi over 2. I'm coming up to the 5th tick mark, so this should be our last one. 6 pi over 2, but this is a good opportunity for a check as well. 6 pi over 2 must equal 3 pi upon simplifying. And yeah, that means we're in good shape. We did start at 2 pi over 2, which is pi, and we did end at 3 pi. We ended at 6 pi over 2 written in, but we're at the right places. So we've got it, folks. We have the horizontal axis nailed down. Next, we need a vertical axis, and we can drop it, say, right here. With the vertical axis, the next most pertinent thing we want to look at is amplitude, definitely. The amplitude is 3 on this one, and it's going to tell us the maximum value we obtain is all the way up at height 3. The minimum value we obtain is all the way down at height -3. And finally, we're about ready to start. We're plotting a sine curve. And so right here, if it's a sine curve, it would be starting right on the x-axis. So here's our first point. But now we have to make a choice. Does our point go up or does it go down? Anyone see what situation we're in for this sine curve? Absolutely. On default, it's going to be up. And this one is actually changing. I like the way you said that. Because of the -3 right here, that's a reflection. It's reflecting your entire sine wave this way across the x-axis. Our curve is actually going downwards as opposed to upwards. Let's put a quick note on there, since that's always very pivotal on our graph. So due to that negative right there, starts by going downward. And we need to know that the default graph, it goes upwards itself. So that's how we're going to resolve that. It truly starts here. We're just falling back on our knowledge of this graph right here for the sine wave. We knew it started at the horizontal axis. We expect it to go up, but if you throw a negative coefficient right in front, it's truly going down. So here's our next point. 3 pi over 2, we hit a minimum. 4 pi over 2, we're back to the x-axis. 5 pi over 2, we're at a maximum. And at 6 pi over 2, back to the axis. Now notice everything in gray, we have found the coordinates of the maximum value. It's right here, it's at 5 pi over 2, 1. We have the coordinates of the minimum value, it's at 3 pi over 2, negative 3. We also have the exact x-intercepts. They're at pi, at 2 pi, and at 3 pi. So last thing to do is actually sketch the curve, and it would look about like this. Doesn't have to be perfect. It looks like my hand got shaky over here, but there it is. That's y equals negative 3 sine x minus pi. So that's the wonderful world of plotting trig functions. Any questions about plotting this one here, folks? Okay, I do have a question, and it would be, what is a good check on this? That's a tough question in a certain sense. Definitely a great way is just calculating it. And there's a couple things you could go along those lines. Say, you could take 4 pi over 2, plug it inside here, do the order of operations, and show you really hit right there, 0. That's calculating a little bit hard. That'd be like a check in an exam situation. If you're doing this check as a homework, I would calculate it out this way. Let's wipe out all this stuff. Now the check is kind of picky, because to get this curve down right, it had to start at pi, it had to end at 3 pi. And so we need to convey that when we go to plot this function. So if you like using graphic calculators, here's how it would go. First, put that in verbatim. Y equals negative 3 sine x minus pi transforms to pi. But next, we need to put in a domain condition, because we don't want that curve conflated with this. We're doing just one cycle. This is many cycles. So we go to the start, put in a curly brace, type pi less than or equal to x, less than or equal to, go up to 3 pi, another curly brace, and this is the check. Your curve should look about like this. If it matches up, you're probably in great shape. We have to be exactly at pi right here, and it does show an exact pi value here, here, and here. So it's a great check because it gives you what you would expect. But word of warning, it's not something to rely on for the homework, because we need to know how to do it this way in the homework. That's how it's going to come in as an actual exam question. So don't over rely on the check, only use it to literally check it out, and you'll be in great shape. Well, that's our first one down. Our goal for these notes is just to practice a couple more, getting fluent with how all this goes. And with the actual exam handout, this is pretty much exactly what we did, organized in this way. It works for sine and cosine in the same exact format. So let's try it again for our cosine function next.
So do we need to write like domain and arrange domain and yeah?
Only if it asks for it in the exact problem right here. There'll be some problems in 6.2 where I would ask for that. So those kinds of questions are coming down a little bit later.
Okay, thank you.
Other questions about that? Okay, but since you asked, that's a great question. Any kind of transformation like this, it turns out it would not have changed the domain. The domain is still all real numbers using that symbol. Sorry, say again? Oh, gotcha. Sorry, say again? In writing mode, or you're saying with the digital ink or something else? Oh, I'm sorry, I'm not too sure. That one's probably a little bit too advanced for me. That might have been it, yeah. Also, the related question on this one for your question there, Hayes, is The range on this one is not actually the same. Anyone see what the range would be if it was a question on this problem?
Is it from like pi to 3 pi?
Not quite, because when we're thinking about range, we're thinking about the extent of the second coordinates or on the horizontal axis. So range on this one would go down to the minimum of -3 up to the maximum of 3. But actually, it's the amplitude right there that's kind of indicating to us what the range would be. An amplitude of 3 just automatically tells us range is from -3 to +3 in that way. But again, I usually don't ask these related questions if we're doing a full sketch like this. I'll ask domain and range questions on different kinds of problems coming up down the line. Well, other questions at the moment, folks? Okay, well, let's take a look at this next exciting function. Same exact instructions as before. We want to find amplitude, period, phase shift. Then we're going to determine where a cycle starts, where it ends, and the increment. And this one's interesting. That starts off with no leading coefficient in front of cosine. That affects the amplitude. We can say immediately on this thing that the amplitude is just equal to 1 exactly. That's because there's nothing in front. So from no leading coefficient, that's our foregone conclusion on this thing. Next thing we want is our period. This one gets a little bit tricky because period is going to involve the pi/6 right here. So whenever you're thinking about period, look to that number. It's involved just all of a sudden. They'll start by saying period equals 2 pi, but then whatever that number is, it'll divide into your period. So it's 2 pi divided by pi/6. We want to simplify this as much as possible. This is 2 pi times 6 over pi. The pi's cancel, and we just get a period of 12 altogether. So that takes care of the period. Next is phase shift. On this one, phase shift is even trickier, because when phase shift is involved, sure, it's going to use pi/3, but it will also use pi/6. And at the same time, we have to flip that coefficient there. If it's positive, we're changing it to negative. So let's write this one out. PS to stand for phase shift. First thing I would look is whatever that sign is, flip it around. So we're at a negative. Negative pi/3 carries in. But pi/6 also affects the phase shift. We have to divide pi/6 into that quantity. And that's what the whole thing would look like with the color coding. So let's simplify this down as much as possible. It's negative pi/3 multiplied by the reciprocal, 6 over pi. And the pi's cancel, 3 goes into 6 twice. Whole thing is -2. Next one is kind of a freebie, and honestly, if you skip that one, it wouldn't matter in this problem. I don't think I'd take off points. It would matter on this one, because this one does have a midline equation at y=5. So probably the best habit is just to say it on each one of these, just to make sure we cover all bases. Midline. It's always an equation that starts with y equals, because it's a horizontal line. And if there's nothing being added, think of this as literally a +0, and that's what's giving you the 0 there. We'll delete that in a moment, but that's the thought to connect for the midline equation. So after we get through all of this stuff, then we just want to say, where does the cycle start? Where does it end? And what's the increment for this particular function? Any questions with this first information here? Okay, let's go for the start. This is where we're going to start our plot. And it's always equal for these functions to the phase shift exactly. So we'll just drop in phase shift of -2, and that's where our plot will start. The end of the plot goes like this by formula: phase shift plus your period. So we just bring those two pieces of information together. Phase shift we put in as a -2. The period over to the left in green we found to be 12, so substitute that in. And that tells us altogether Our plot ends at 10 exactly. So that's all good and helpful information, but the most helpful bit of information next is this. Increment, if for these functions, is 1/4 or 1/4 of whatever your period happened to be. So on this one, it's 1/4 times, lucky for us, it's a period of 12, so that divides evenly. I'll try to always do that on exams, just so we're not hunkering down with fractions in an exam setting. I like to make things divide evenly and nicely. Not a guarantee in homework, so we'll see ones like this one below, where it's not as nice. So this will be 1/4 times period of 12. 4 will go in there exactly 3 times. And now we know how much we should move to the next tick mark in order to get all these interesting features up here in the plot. This gives us this information highlighted in gray. Well, I think we're ready to start. Any questions so far, folks, with the preliminary analysis? Okay, now we're ready to plot. First thing we want is a horizontal axis. So we'll just draw a really long one. And again, it's a good idea to not even put the vertical axis just yet until we know where everything lies. Let's first go and put down this -2. That's where the cycle starts. We're going to be adding 3 repeatedly, so let's highlight that. That's going to give us all of our next most important coordinates. So -2 plus 3 takes us to a 1. Plus 3 will take us to a 4. Plus 3 takes us to 7. And plus 3 again takes us to 10. It's not going to be a perfect plot because I don't have a perfectly steady hand. Some of my intervals are not of equal width. Let's leave it like that. Your plot doesn't have to be perfect, and we can convey that by leaving it the way it is. The vertical axis now is about right here. Let's make it actually vertical. One last try. Sorry, say again. Oh, I only put it here because it looked like it was closer to the 1 rather than the 2. So here I'm at -1 is what I was visualizing. And here I visually estimated must be 0 then next. But one important comment there is, it truly doesn't matter at all where your vertical axis is. If you moved it way out here, I would just have to assume that's not the origin, put the right values here and here, and you still have an accurate plot. So if these move way away from the origin, you don't have to have like a long line going to show the vertical axis. You could just move it to wherever it seems appropriate. And I think this was about here or so. Maybe a little bit more to the right. There we go. Other questions so far? Okay, next thing we need is the vertical axis. But to settle the vertical axis, that's all about the amplitude. If the amplitude is 1, we're going up to a 1 here and down to a -1 right here. So we're just about there, folks. Now, next thing we look at is right here. And notice how I circled there. You want to look if there's any negative sign, definitely, on these kinds of things. But it looks like this is an ordinary cosine function. So put the mental image of what that looks like. Let's scroll just for a cheat sheet. We're placing this curve onto those locations that we marked off on the horizontal axis. And because the sign is positive, we'll use it exactly in this format. We'll start at its peak. If that was a negative, it would have started at its minimum. So back down to this. We have cosine and it's positive, so we're starting right here. We need to begin where the cycle started at -2. So our first point is in this location. Because we put in a maximum value, cosine can only do one thing, it has to go down. So right here at this tick mark, that's where our x-intercept is, exactly at 1. It keeps on going down, so here's our minimum value. Then it increases thereafter. At 7, we have an x-intercept. And at 10, we're back to a maximum. And keep in mind, it's not a perfect plot. The distance here to here should be the same as this distance. Looks like I just had a shaky hand drawing it. But all that's completely forgivable. I'm not expecting a perfect plot when you do these by hand. Last thing you have to do is throw in the curve. Cosine goes about like that. That means we did it, folks. This is y equals cosine pi over 6. times x plus pi over 3. And we made it just barely in time. I don't think I was looking at the clock too carefully. We got it in with time for questions. Sorry for going right to the minute on this one, folks. But any questions on the conclusion for this problem?
So for this one, like the domain would be the real number and the range, it will be like 1 to -1. -1.
Yes, absolutely. So for this particular curve, because there's no change to the amplitude, same exact conclusions like what you saw here for cosine, absolutely. Other questions so far, folks? Okay, oh, well, looks like we did run out of time. Again, sorry for going right to the minute. If you do have additional questions, I'll be happy to help out. But what we'll do when we come back on Thursday is we're going to take on the next plotting one, and then we'll go over to section 6.2, where we'll see how to plot the remaining 4 trigonometric functions. Well, have a great night, folks, and I appreciate you all making it in. Again, this is kind of a tough class to make with sports and Valentine's Day all going on at the same time. Have a great night, and I'll see you all Thursday.
Thank you.
Thanks, folks.